welcome back. So let's continue this process of talking about minerals, resources, how they get put in place. So there's magmatic processes, which we talked about in the previous video, and then also hydrothermal processes. So these type of deposits are produced when groundwater is heated up naturally, either by coming near or in contact with an igneous body, some sort of igneous intrusion, some sort of magma intrusion, or by just circulating down to great depths. If water can, for some reason, make its way down deep, the deeper you go, the hotter it gets. But in any case, all these have to deal with hot water, because such hot water can dissolve valuable substances throughout a large volume of rock. So you get kind of water, when it heats up, when things heat up, they rise. So when hot water is heated up, it begins to rise. As it's percolating through the rocks, it can really dissolve out any valuable substances and bring it with it as that water continues up. And if that water makes its way into any type of area, as it begins to slow down and cool down, that dissolved substance, that dissolved material from the hot water precipitates out, kind of falls out. The hot water, it does a good job of keeping it, chemically in place, but once that water cools down, it just can't really hold on to that hot stuff anymore, so the minerals kind of precipitate out, fall out. Now, depending on where that hot water goes will determine if it creates a deposit. A lot of times, water wants to find cracks, the easiest path up, and it finds cracks. It finds places to go. A lot of times, those are at faults, areas where the crust has been cracked. That natural fault can create a pathway for water in some cases. But in any case, there's a couple of different hydrothermal processes we'll talk about. Volcanogenic massive sulfides, or known as VMSs, and porphyry deposits. These get a little complicated, so just sit back and relax. So volcanogenic massive sulfide, VMS. Again, hot fluids circulating above a magma chamber at or near mid-oceanic ridges. All right, so these are kind of hot water circling around mid-oceanic ridges, can really scavenge elements like sulfur and copper from the rocks through which they pass. I'll show you a diagram here momentarily. As this hot water is circulating through the ground and coming back out of the ocean surface, as that water begins to cool down, once that hot water hits the ocean floor, it comes out into the bottom of the ocean. It's cold, it cools down. All that material that's in there that's been dissolved begins to precipitate out, begins to fall out. Commonly, if we're finding these types of deposits, they contain copper, zinc, lead, gold, and silver. Now, we're not talking about going down to the bottom of the ocean and mining out near the mid-oceanic ridge, mining out near a divergent boundary. No. Ancient boundaries, that are now on land due to plate tectonics, this is what we're mining out. Right? We're not going down to the bottom of the ocean right now. It's too deep. It's not worth it. But on land, we do find evidence of, this used to be ocean bottom. Due to plate tectonics, plates move around, rocks get pushed up, rocks get pushed down. For instance, all around Arizona, a lot of the sedimentary layers around here were formed in the shallow parts of the ocean, meaning that Arizona was once under the ocean. The layers of the Grand Canyon, these are sedimentary rocks. They wouldn't be there if the ocean hadn't covered that area hundreds of millions of years ago. All right? So again, we're not talking about going down to the bottom of the ocean now. We're talking about when this type of formation occurred. This is how this happened. Now it's on land, and we can mine out this area with an understanding of this is the process that occurred hundreds of millions of years ago, or even billions of years ago. For example, right here in Jerome, Arizona, right in central Arizona, it's a good example of these VMS deposits, meaning the area in which Jerome is, at one point, was underneath the ocean, tended to be that area near some sort of mid-oceanic ridge, near some sort of divergent, pulled-apart boundary. So here's kind of how they work. All right, so this is the bottom of the ocean now. So you get water, kind of cold water percolating down into the seabed. It gets heated up by some magma source. Again, so if you're near a mid-oceanic ridge, so that's going to be a divergent boundary, magma is going to be a little bit closer to the surface, because as those plates pull apart, magma wants to push up. So as this water is circulating down, it gets heated up. It starts to scavenge minerals and other valuable resources from the rocks that are around it. That hot water comes out of what are known as black smokers because it looks like black smoke is coming out. It's just hot water filled with a bunch of debris, essentially. And so as that material comes out of these black smokers, it hits the ocean water, which is very, very cold. That material cools down, so material is deposited just on the outskirts of these black smokers. So you can find copper, zinc, and lead, iron. Oftentimes these are mixed with sulfur chemically. So when we extract it out, we have to extract the copper or the zinc or the lead or the iron from the sulfur. So they're kind of molecularly embedded in there. But if you've ever been to the town of Jerome, the haunted town of Jerome, the reason Jerome is here is because it was a mining town 100 plus years ago, and the reason it was a mining town is because there's a large VMS deposit here, and you can kind of actually see the old volcanic massive sulfide. The yellowish tinge to a rock is a good indication that it has sulfur in it. So Jerome is here because of that. So the copper mine was due to a VMS process. Here are some volcanogenic massive sulfide deposits around the world. So again, these areas indicate that these processes had occurred. Again, here in Arizona, in Jerome, kind of near Prescott, near Kingman, we see all these processes that have occurred. So we have these VMS deposits, but then also something called porphyry deposits. Again, still hot water, but circulating through and around igneous intrusions. All right, so these are igneous intrusions into more continental crust. We're not talking about magma bodies below oceanic crust. So we have hot water circulating through the ground, so through and around these igneous intrusions, typically on continental crust. Again, scavenging metals from both the intrusion and the surrounding rock. When these fluids kind of make their way up and inject into open fractures like faults, again, they cool down. The further they get away from these hot bodies, they cool down, and those minerals precipitate out. Again, rich in copper, zinc, lead, gold, silver, tin, mercury, and molybdenum. The largest mines on Earth are porphyry deposits. So the biggest mines that we see on the surface of the Earth are typically these deposits, because these deposits are characterized by the presence of low-grade, lower concentration, disseminated ore minerals. So they're lower concentration and they're spread out over a large area. There's still a concentration factor high enough to be valuable, but it's on the lower end of that spectrum. So usually lower grade, really spread out. So you really got to dig this stuff out of big pits. So how does this occur? So typically at convergent boundaries, as the oceanic crust is kind of being pulled down, it brings with it a number of different things, including water. So that water is kind of mixing in with the magma. As that stuff is making its way out, that water can be driven off by the heat from the igneous rock, or if there's any water circulating around, it gets driven off as it kind of makes its way out of or away from the igneous body into typically faults or cracks or fractures. It can deposit copper. So here's another kind of look at that as well. Yeah. So not only can you get the porphyry deposit right near a large kind of magma intrusion, some sort of igneous intrusion, but that hot water can also continue, typically up faults, alter. It's such hot water it actually alters other existing rocks, creating a kind of a weird form of metamorphic rocks. We could also further leach out copper and take with it and deposit copper in what are known as skarn deposits, so porphyry and skarn. But these magma chambers are so large, and you get so much water kind of percolating through and around it. This area is really spread out, so you have a very large area to mine out. So low concentration, low grade, but it's a very wide area. So you're digging these massive pits to mine out this porphyry deposit, porphyry copper, porphyry gold. Here's just an example of where you find these things. So oceanic arc, convergent boundaries between two ocean continents, ocean continent and ocean crust and continental crust colliding. You get a lot of, again, porphyry, copper, and gold. Cu is copper, Au is gold, plus skarn deposits. Back arc extension, so places where the crust is also extended, where you're creating fractures, can also bring magma closer to the surface. If there's water circulating through there, can also create these porphyry deposits. So in essence, you need places where the crust is broken. Large areas where the crusts are broken. And that typically happens at kind of convergent boundaries or even boundaries that have been pulled apart. I want you to think back to how Arizona formed. We talked about this a long time ago, but there was convergent properties at one point, but the vast majority of Arizona in the basin and range formation was formed due to crustal extension. So that area, this area of Arizona, kind of the middle to southern part of Arizona, extended apart when the boundary off of the west coast changed. So you get this, what's called a back arc extension, and you do get some copper deposits and gold deposits. You're creating these cracks and magma to get closer to the surface. You're thinning out the crust. Magma is getting closer to the surface. You're giving it conduits for water to kind of creep into these cracks. Again, it's a complicated process, but this really creates very large areas that have copper deposits. So this is one of the largest copper deposits, copper mines, I should say, on Earth. We'll look at this in lab a little bit, but just to show you, give you a reference here, you see this little dot down here? That's actually one of these giant vehicles compared to a full-size truck. You can see, I mean, these things are 30 feet tall or so. Yeah, 20, 30 feet tall, and that is this thing. So you can see, you can imagine how big this mine is. This is also the area of some landslides. You can see a landslide here, a landslide here, and I believe we talked about that in class a little while back. So anyway, so here's an area of porphyry deposits. Again, kind of note where these are located. All right, look at where these are kind of located, North and South America, where they're kind of located through Europe and Asia. So note where these are located. In Arizona, again, most of these porphyry deposits kind of in the middle, southern portion of Arizona, in that basin and range portion where their extension has been, where there's cracks for this hot water to make its way through and deposit material. None up here. All right, remember this, the process of the Colorado Plateau appears much different. This area of Arizona formed much differently than middle and southern Arizona. But again, just keep an eyeball, looking at where these deposits are, and again, looking at a map of plate tectonics. Quite interesting where these deposits occur. Again, what kind of boundary do we have here? We saw a lot through this part of Europe and this part of Asia. What kind of boundaries do we have here? Interesting. Again, porphyry deposits in Arizona. A lot in the basin and range, some in the transition zone, really none up here in the Colorado Plateau. Again, this area pulled apart, cracks, faulted, allowing for hot water to easily make its way through. And when we're looking at Arizona, the biggest porphyry deposits are over here in what's known as the Copper Corridor. So kind of if you go, let's see, that'd be east of Phoenix. So if you're traveling out towards Globe, Miami, Superior, so in that area, that's the Copper Corridor, where there are a lot of copper mines. There are other copper mines around Arizona, but this is kind of a main concentration of them, kind of again in this area right here. All right, complicated information as far as VMSs and porphyry deposits, but at the heart of it, it's just hot water circulating through rocks, leaching out, dissolving out valuable minerals, and when that hot water gets into these cracks and gets further away from its heat source, some magma body, some source of heat, it cools down. When that water cools down, anything dissolved in there begins to precipitate out and kind of gets stuck in these cracks. And so when we're mining, a lot of times we want to find faulted areas. That's a great place to look for, example, copper or gold. We'll pause here. When we'll come back, we'll talk about a couple more types of deposits, sedimentary and placer deposits. See you in just a minute.